I'm Lidia Lonergan from Imperial College, and I'm privileged and honoured to be able to chair this session this afternoon. And we're moving from ocean subduction zones sort of finally, or onto the continents. And we'll stay on the continents for the rest of the afternoon. So the first person this afternoon is our keynote, John Dewey, talking about plate tectonics and the geology of plate boundary zones. So if I may just say one little anecdote, John. I don't know, I have lots. John was my PhD supervisor, so there are lots of things I could say, but I'll restrict myself to one. I first heard John talk in 1998 in Trinity College in Dublin, and he came to give a keynote talk that evening on his current theme, which was extensional collapse in origins. And we had got one of the biggest lecture theatres in the university, in the arts building. It was full. There were people from the two universities in Dublin, people from the Geological Survey, and I expect people from around the country. And that was, if any of you know Irish geology, there are basically no rocks younger than the Carboniferous or the Pennsylvanian. So anything you ever studied was to do with the Caledonides. And John, as was mentioned yesterday, his fundamental contribution to all of this debate, along with Brian, was actually on applying this marvellous new exciting theory to what happened on the continents. And one of the difficult challenges was obviously the Caledonides, the Iapetus Ocean before the Atlantic, and John, had seminal ideas that were of great interest in Ireland. So, to get to the point, he was scheduled to talk for 50 minutes, he had 10 minutes questioning. An hour went by, John was still in full flight. An hour and 30 minutes went by, and he was still there, and there had been no mass exodus. So, anyway, over to John today, and you have 25 minutes, and the clock is starting now.
Lydia was one of the fiercest graduate students I've ever had, and she clearly still is. Now, Walter Pittman and Haxby and several other people and I designed and produced this map in 1973 or thereabouts. And we call it, rather arrogantly, the age of everything. And you can see that there's absolutely the fundamental difference between the oceans and the continents are beautifully expressed in this diagram. It shows that plate tectonics looks like it produces a rather simple result of a strong, relatively strong lithosphere with very strong torsional rigidity, going back to about 160 million years, generated the ridges and subducted and lost in the trenches. And you can see that the continents look rather different. They are the geology is very, very complicated, as any geologist with boots and a hammer knows. And going back to Jim Bryden's point, plate tectonics wasn't made a mess by geologists. The plate tectonics made continents a mess, as we'll see. So this enormously complicated pattern was facing us. And geologists tended to be very conservative people who mapped an area and they got involved in a little bit. And something very important happened to me in 1965. I'd just been appointed as a young lecturer in Cambridge in 64. And Tusa Wilson came on sabbatical for the 64-65 academic year. Harry Hess was also there at the same time. And they used to come into the Sedgwick and chat and have coffee and so forth. And I learned an enormous amount from Tuso, and also at the same time from Teddy Bullard. Teddy Bullard, I won't go into the details of this, but he helped me in my career enormously just by being a very kind and gentle and thoughtful and suggestive man. But anyway, Tusa Wilson used to come into my room, and one day he came in early 65, and John, I've discovered a new class of fault. And I said, nonsense, we know about every kind of fault that exists on the surface of the Earth. And he showed me his now famous model. He opened it and closed it, and I did this, and I suddenly realized I was in the presence of a very clever man. And he said, I'm not only that, I'm producing a new global tectonic map with trenches and ridges and transforms and subduction zones. And later in the 70s, Kevin Burke and I were talking to him and said, if only I'd known Euler's theorem at the time, I might have, on a sphere, I might have had the whole theory in 1965. But here he was, producing, he called them plates, and he recognized their main character. But the thing he did for me mostly was not just teach me this, and Harry Hess the same about C-frost spreading and so forth, but also get out of your little local environment in the west of Ireland. I was obsessed with the west of Ireland. I loved it. It was a thing of beauty for me. And I was mapping it and looking at it and in great detail, and the petrology and the geochemistry, everything to do with every kind of rock there. And I was becoming a little sort of constipated about this little area, I think. So basically to say, get out, say, go to North America. The Appalachians, obviously, if you close the Atlantic, the Appalachians clearly go on as a continuation of the Caledonides. Spread your wings a bit, go on to the Appalachians. And what happened at the same time, roughly the same time, Charles Drake was in he came and went quite a lot. Charles Drake from Lamont, Columbia, was in Cambridge, and he was a very important figure in that for me, he said, look, John, I can give you some cash, and if you'd like to come to Lamont anytime you want for short, long periods. And I started doing that. In 66, I went across for a period in the summer, and I got to know Walter Pittman and Lynn Sykes and lots of people who became very important in the science, were very important in the science, and they gave me tutorials. So I used to flit back and forth between, and then I went on a long sabbatical in 1967, and I used to flit back and forth between Cambridge and America, and in terms of my office site, and also in terms of my geological site, I started working in Newfoundland. And I went down into the Appalachians, and it became very exciting. So the two became melded, and I was caught up, this poor innocent young lad was caught up in a maelstrom of geophysicists, both in Cambridge, and I was berated by all sides in many, many ways. I was encouraged tremendously by the geophysicists to expand and start doing geology in relation to the new global tectonics. But the geologists in Cambridge were extremely suspicious of my dealing with geophysicists. They didn't like it at all. Whenever I said I was going down to Madingley Rise, they tutted and said, it's dreadful, he's a traitor. And the other thing was that in Lamont, of course, Maurice Ewing, was basically a non-believer in plate tectonics. I mean, I was taught plate tectonics as a fact as an undergraduate, and it was normal to me. The thing about plate tectonics, or not plate tectonics, but the oceans, and opening up between continents moving, is that geologists would go to the edge of the ocean, peer into it, and it was a big blank. And also, they didn't care. It didn't matter. Oh, yes, continental drift was happening, but it's not relevant to us. We're dealing with the detail of continents. Okay, enough of that general kind of introduction. So, there's a nice picture of Tuesday. This is the man who really changed my career very strongly. But I want to mention also a number of geologists. I should say at this stage that if you had 1 million geologists for 1 million years working on the continents, they would never discover plate tectonics. How would you take all this incredible mess and make a plate tectonic picture? Argonne tried. In terms of the collision of India with Asia, realized the Himalayas were the result of that collision. But the bulk of the geology of the continents was very obscure and very difficult, and there are all kinds of weird and wonderful theories like the geosyncline and all those sorts of things had developed to explain it. So necromancy, geonecromancy, you might call it. But we had lots of data. We at least had lots and lots of data. Geologists traditionally have liked complexity. They don't like things being simplified too much because it sort of does them out of a job, I suppose, eventually. But anyway, here I was and starting to look at plates, looking at the new global tectonics. Here's a partial list of some of the geologists who've had a very big influence on ideas in tectonics with time. And some of their ideas were harbingers of ideas that became important in plate tectonics. And I'm going to mention just a few of them. There are many more than this, actually. And let me just go through them. The first is Harry Wellman. Harry Wellman is a Brit who went across to New Zealand in the 30s and became a sort of roving mapping geologist, both in universities and for the survey. And he basically discovered the Alpine Fault. The Alpine Fault of New Zealand, that is. And he recognized that the Alpine Fault, which runs here, had many hundreds of kilometers of right lateral motion on it. It was also a bit of a thrust as well. He realized it's transpressional kind of structure. And he realized also, or suggested, that the motion on the Alpine Fault has to end somewhere, has to be sucked up somewhere. And he suggested that it's sucked up at one end by the Pusagar fold belt structure here, the trench, and was sucked up by the Hikurangi Trench, or at least its ancient equivalent in here. So he really invented the trench-to-trench transform, although he didn't call it that at the time. And then, of course, here's a wonderful thing that an outcrop that Harry described very early on. It's a place where the lower crust of the Alpine ranges These are garnet granulites, garnet amphibolites, lower crustal rocks. Sorry, I've done it already, of course. Have been thrust over what the Americans will call dirt. It's basically it's young Holocene gravels. The lower crust is being thrust across lower. I mean, this is an extraordinary outcrop and a recognition of that for the time. Tim Little has done some wonderful work subsequently to illustrate this whole concept. The next person I should mention is Tom Dibley. Tom Dibley was an extraordinary man who mapped during the 20s and 30s, probably most of California. He was an extraordinarily persistent boots and hammer man, and he discovered the southern continuation of the San Andreas Fault. Andy Lawson, in 1895, wrote a wonderful paper on the northern part of the San Andreas from San Francisco northwards. He discovered the southern part and recognized that it had a truly massive offset of many hundreds of kilometers. So here are two of the big ingredients of plate tectonics recognized before the Second World War. And there we have the San Andreas. Andy Lawson recognized this bit that broke in the 1906 quake north of San Francisco, and here we have the southern branch, and he recognized again. And also, Dibley also referred to this strange big bend in the San Andreas, which of course is a transpressional bend, and that's why the transverse ranges are there. So this is a very important contribution. The next one I want to mention is Bert Quinnell, a New Zealander, who mapped mostly in the Middle East, in Jordan. And he got the gold medal from the King of Jordan for studying Jordanese geology. And Bert Quinnell was quite extraordinarily clever geologist and wonderful mapping there, but also recognized that the Dead Sea transform, or what we now call the Dead Sea transform, done it again. The Dead Sea transform, the Dead Sea fault, was a left lateral fault with about 112 kilometers of displacement that clearly ended at the northern end of the Red Sea. And he said, here we have an interesting situation. If you plot longitudes normal to the Dead Sea transform, they all intersect at a pole somewhere at a point somewhere near Gibraltar. He said, this must be the pole of rotation around which the Arabian Peninsula moved with respect to the African plate. And moreover, he said, this is what Jason did later, of course, and he also said that the motion on this 112 kilometers of left lateral motion must be sucked up by extension in the Red Sea. So there's another important component. Alan Smith, who sadly just recently died, was a very fine, trained as a physicist, and he became at Princeton a field geologist, and did a wonderful PhD on the Belt and Windermere series of northwest Canada. And then, of course, he got very interested in the early phases of computing in Cambridge, of the Titan and so forth. And he was really the first to, with Bullard, Everett and Smith in 1965, to make a wonderful reconstruction of the Atlantic Ocean, north, south, and so forth, but using Euler poles to make the reconstruction, a finite difference method of using Euler poles. Now, and there's his reconstruction, or the Bullard, Everett and Smith reconstruction. But the one above all I really want to mention, and it's not that the others aren't good, they're all wonderful field geologists and they made these great contributions. The one I really want to emphasize strongly is a man called George Plafka. George is not known very strongly outside, except for one very important paper, and it's very important. George, in his career with the USGS, mapped almost, not the whole, but he mapped huge terrains in Alaska, terrains with an AINS at the end, in Alaska. And he also recognized that during the 1964 earthquake at Anchorage, or near Anchorage, he drew this cross-section. It's quite extraordinary for the time. What he did was to take the earthquake, about 30 kilometers or so, and said, there must be two nodal planes, they must be steep, thrust, high-angle reverse fault nodal plane, or there's a flat nodal plane. You've got to make the choice. And he said, look, the aftershocks occur along the flat one, and also when you look at the steep one, which most of the geophysicists, I have to say, at the time chose, the strike length of this was about 200 kilometers on the interface it's a very big earthquake on the interface. And he said, look, if had the steep nodal plane been the plane on which that moved to produce the fault, there's no way that could not have broken the surface. But what it did at the surface, of course, was to cause tremendous areas of subsidence and uplift, according to the dilational and compressional quadrants of this load. And moreover, he said, look, this plane of earthquakes points straight towards the bottom of the trench. This must mean that the Pacific Ocean floor is slipping underneath Alaska. Now, that's the proof of subduction, a flat subduction, if you like, and that was George Plafka, 1965. But one person I do want to mention, not a field geologist by any means, but I want to mention the work of Tanya Atwater, who wrote the first paper, probably the most important paper ever to link plate tectonics with geology. Tanya produced a wonderful piece of research that related, and this is simplified horribly here, of course, that related the magnetic stripe history of the Pacific Ocean to relative motion and the progressive growth of the San Andreas Fault between two transforms. And she showed, by plotting the ages of the volcanism along this thing and the various variation offset along the fault, she was able to show that that fault had to elongate as the two transforms and migrated south and north. And, I'm sorry, done it again. And you can see that the volcanoes progressively shut off northwards and southwards. Lassen, I think, is probably the last of the volcanoes here. A wonderful, very, very clever piece of work. And this kind of approach to quantitative plate tectonics and linking geology in a general kind of way to those relative motions was taken up by Walter Pittman and me and Alan Smith and various other people in dealing with the Alpine system a few years later. Now, what I want to do now is to actually just show you very quickly two things that have pleased me very much. I can't deal with the whole of geology and plate tectonics in half an hour or 20 minutes or whatever it is. So what I've chosen... I know. So what I've done is chosen two pieces of work that have pleased me very much. And one at the beginning of my career, starting with the piece of work I did in the Appalachian Caledonian Belt, in which at Lamont, in the years 67, 66, 67, and 68, I basically produced a tectonostratigraph of the Appalachians and the Caledonides, and a series of tectonostratigraphic charts. And here's part of the first map I produced. I've closed the Atlantic, of course, to get it up. And we saw a very strong correlation between structures of the Caledonides and the structures of the Appalachians, as you would expect, of course, had these two been together. Okay. And what I started to do was to design a series of tectonostratigraphic charts. That's simply taking the stratigraphy and the various events that have happened, the deformations and so forth. And I don't want to get involved in the details of this. But what I want you to notice is that I've coloured various facies, different colours. These colours down here, the yellow and the oranges, are basically big rift complexes, places where the continental lithosphere has been pulled apart. And indeed, I should mention at this stage, some of which we've actually tried to reconstruct and use the McKenzie basin model for this, and it works rather well in some of them. And then I've also shown, in the blue, things that look like a continental shelf with a facies change at its edge that suggest the edge of a continent and the beginning of the continental rise and oceanic rocks. And then outside that, we find, in each case, each of these various cross-sections, shown in this orangey colour, we find a dark orange colour, we find arc rocks. Clearly rocks, andesites, dacites, and rhyolites, and sometimes basaltic andesites, that clearly fit our present observations of the extant arcs of the world. So here we have a situation, we have a continent, and suddenly we realise there's an arc adjacent to it. Did that arc build there, or did it somehow come in and collide with it? With a couple of my students, some of our students in Albany later, showed very clearly that there was a collision. We thought at that time, Jack Bird and I and various other people, thought that in fact there was a marginal basin that had closed and pushed the ophiolites out over the edge. So ophiolites were always tied up in some way with the zone between the arc rocks and the continental margin, continent rocks. So this we did all along the Appalachians. And we started getting involved. I started mapping in Newfoundland in some detail, seeing one, as Jack described earlier today, wonderfully abducted ophiolites, and we had this clear, huge sheet of ophiolite that was abducted to cause the tectonic orogeny. And we thought something similar may have happened to cause the Grampian orogeny in Scotland and Ireland along strike. And what became clear also from the work of students in Albany mostly is that there are two sets of arc rocks. There is an older set that predate the tectonic orogeny. It looks like an arc constant collision. And then there's another set of arc rocks on top, slightly more silicic perhaps on top, that probably represent the flip in polarity flip in polarity of the subduction, and the new arc built on top of the whole lot to produce, if you like, an Andean kind of margin. So here's one way of converting an Andean margin. It's converting a continental margin into first of all, an orogenic belt, and then into an Andean margin. These are the kind of ways in which we were beginning to think of the system. Here's the thing that I drew in the late 60s, early 70s, and that simply shows the concept of the flip in polarity and the age of two arcs associated. Well, I want to very quickly now describe the geology of... Sorry, I'm not allowed to move from there, am I? I want to describe the geology of this area of the Caledonides in the west of Ireland, very, very briefly, to show that you can have orogeny below sea level. In fact, orogeny below an arc. And that's what I'm going to show you now. Okay. Here is a very simplified structural map, or tectonic map of Western Ireland, in which, very, very simply, we go from the Dalradian rocks, which are rift-related and continental margin-related rocks, through a series of what we now know as it's a blue schist zone in here, which is probably the suture between this arc and the continental margin. There's then a group of accretionary prism rocks with a backstop of an ophiolite, and then there's a four-arc basin with huge thick pile of sediments in, and then, strangely enough, we come back into the Dalradian in Connemara. And we thought that was pretty strange, so we thought for many years that this was a terrain that somehow slid in sideways. We now know that to be incorrect. What it is, as I'll show you on the next one, there's Connemara. Connemara, the Dalradian rocks of Connemara, are basically a huge pile of north verging and north-facing naps with a Barrovian metamorphism, and we've got kyanite, staurolite, and andalusite in various parts. So we've got a triple point somewhere in the middle of Connemara. So here we have this set, and in the South Mayo Trough, this Ordovician four-arc trough between this very tiny arc and the continental margin, we find a most wonderful stratigraphy you can take apart. And what we find in that stratigraphy is this. Here is the mafic arc. These are basaltic andesites and a few boninites as well. A mafic arc that is associated with the growth, late Cambrian, early Ordovician. On top of that, the arc goes silicic. This is very common when an arc begins to approach a continental margin and you start getting the magmas contaminated with sediments from the edge of the continent going down the tube and getting remolten. In fact, we've got some old zircons here from that now. So the arc goes that, and then synchronous with the arc going silicic, we have the four-arc trough with a massive thickness of volcaniclastic turbidites, plus turbidites coming in from the Laurentian margin, from the Laurentian continent. And we now know that this is simultaneous. We thought for a long time this is simultaneous with the deformation of the Dalradian rocks, the Grampian rocks. What? No, it's not possible. Okay. Simultaneous with the rubbish. So here we have a four-arc basin with no detritus from the Dalradian. In fact, the detritus from the Dalradian origin doesn't come in until up here, like that. So while this deformation is going on, we have an arc adjacent to it. And what we now realize is that the central section is a cartoon section across Connemara, across Western Ireland. What we clearly have, here's Connemara with the north-facing naps. There's the four-arc basin in here, and the arc, and the ophiolites and so forth. There's a huge abducted slab of ophiolite and arc and four-arc basin that has gone across the continental edge, has metamorphosed this system in here. And recently, Paul Ryan and I have quantified this by a simple numerical model. And what we find is this, that if you choose appropriate lithospheric thicknesses for a big rift complex at the edge of a continent and in the age of that rift complex from thermal recovery, and you look at the rocks of the abducted ophiolite and arc, we find that there is no way we can get the thing much above sea level. That is, that the whole of the arc and the ophiolite climb onto the edge or abducted onto the edge of the continent, and basically they are thrust across, they deform the Dalradian underneath, and the heat for the Barrovian metamorphism, the Dalradian, we believe, must come from the hot arc, who was a cenosphere, but beneath which must have been 1,300 or so. And basically, we can show that the modelling virtually proves, we believe, that the Dalradian deformation in the rocks down here was not only below sea level, but it was below an abducted arc. And it only came up to the surface to yield sediment to yield sediment when the arc flipped in middle Ordovician times, and this rebounded, the whole system rebounded, and we started uplifting this, and you started getting Dalradian detritus. So you can have an origin below sea level, no detritus, no nothing. If that had stayed there for any length of time, you'd never know an origin was there. And what is so lovely about this is that once the flip has taken place, in South Connemara, you have a series of accreted seamounts in something that looks like the inner wall of a trench. When you go a long strike, you go through the Longford Down Massif, you go into the southern uplands. And in the southern uplands, I've taken the work of Phil Stone, stratigraphic work of Phil Stone and Jim Floyd, and I've simply plotted here, here we go from the Laurentian margin, sort of Ballantrae and Ayrshire. This is the late Juristic. Eventually these collide. Iapetus finally closes towards the end of the Silurian. And here we have a series of packages of turbidites. And look at that. They begin in 2 million year increments across like this. Here are some oceanic black shales, the Hartfell Glenkiln shales that Lapworth described. Then a series of turbidites in 2 million year packages, and the growth rate of, if it isn't accretionary prism, well, what else could it be? What could that stratigraphy be other than? And here's a lovely illustration of the relationship between plate tectonics and geology. And it comes out of really looking at the stratigraphy and the fossils incredibly carefully, as Charles Lapworth did. This is really the work of Charles Lapworth, you'd have to say. So that's one. Now, the thing I was going to say, had I had time for it.
Another three. I told you a lie to keep you on straight and narrow. You now have 3 more minutes.
3 more minutes. Okay, I won't have any more slides. I shall just talk, if I may. Now, having talked about an old system, the thing I've been doing, since I went to California after retirement from Oxford, I didn't want to retire, whereas in America you don't have to retire, so I went there for a while. And so what I did was to cast around for something interesting to do. And what was most interesting in California to do, of course, was to look at the neotectonics of California. The advantage of doing neotectonics as a geologist is this. Although you're confined to the brittle field, and being a structural geologist, I love cleavages and sort of gneissic fabrics and all that kind of stuff. But if you can get used to the idea that brittle things are telling you an awful lot about the upper crust, then what you can do is look at the faults and the joints very, very carefully. You can map them out, the characters, the small folds and so forth. You've got the geomorphology, the landscape, you've got the erosion and deposition in basins, you've got drainage, fluvial budget systems you can deal with, you can derive, you've got the seismicity, of course, and then you've got the most important weapon in a geologist's armory. You've got GPS velocity field derivation. And in California, that turned out to be much of the key to looking at the neotectonics of the so-called transtensional corridor. I tell a lie, as you have. Here we are. Here's a very much simplified map of California. What we've done is to look at this little area in here. Okay. Here we have the San Andreas Fault with a big bend. There's an earthquake zone or a deformation zone that runs from the mouth of the Gulf of California, or Palm Springs more like, up the Blackwater Fault system, running up the east side of the Sierra Nevada. This is a microplate or microblock, whatever you like to call it. And then it runs. There's a zone that runs across, a compression zone. You see folds and thrusts in the Great Valley in here, and it runs across to what now is clearly a Mendocino quadruple junction in there. So this we know from the velocity field that this is moving relative to the Argus Range on the east side of the system. We're coming into the Basin Range, of course, in here, and there's the Sierra Nevada in the eastern side of this block. And this is the transtensional zone. We've made an incredibly detailed study of the southern end of that transtensional zone. And what we find there, basically, is this. Transtension causes havoc.
You're out of time.
I'm out of time, okay.
Finish this sentence.
Transtension, thank you. Paragraph. Transtension causes havoc with rocks. What it does, basically, is it comminutes rocks. It breaks them down, it smashes them, blocks are rotating, some with vorticity, some against vorticity. And the ultimate thing is you go from the Sierra Nevada into the core of Coso, and you go from fresh, beautiful Cretaceous granodiorite into a mush. It becomes a mush, almost a fluid mush. So even the simplest kind of tectonics can cause the most appalling geological havoc. I will finish there. Thank
Wonderful.
you. Yeah.
Thank you very much, John. Now we very carefully have a couple of minutes for questions. So, who would like to go first? Gosh, you're all cowed after that. Well, I would just like to comment, I find it amazing that you've spent 50 years on that same tiny little block in the west of Ireland. But hey, it's beautiful. I did my first mapping there, but it's still quite amazing. Anyone else?
Some other kind of geology. Somebody else must have a little story to tell about geology and plate tectonics. Yeah, something there.
In one of your earlier papers, you mentioned neotectonics in Connemara. Would you like to expand on that a little bit?
Can you give your name, please?
My name is Malcolm McClure.
I've been, as I said, Connemara is an obsession with mine. It still is an obsession. And I should just say, at the age of 80, I've discovered one thing in geology. Geology is a disease for which there is no cure. I was hoping to settle down and paint watercolours and write things and so forth, but in fact I can't stop doing fieldwork, and no, I think anybody who likes geology can't. So basically, neotectonics and Connemara, what we discovered in Connemara, myself and McKerrow some years ago, is that one can contour the subcarboniferous surface. And the subcarboniferous surface is clearly quite strongly deformed, and the question is, when did that come up? Well, I take the view of Kevin Burke's view that if you have topography, it's generally fairly recent. You don't get topography that lasts very long on this Earth for various reasons. It can either tectonically or it can be eroded down. So what we found is that we have this surface with all these big faults in them, some with throws of 3 kilometers. And the question is, when did it go up, and when did all this neotectonics take place? Well, we looked at sedimentary sequences off the west coast of Ireland, and they turned out to be big ones were Oligocene, and we were pretty certain this was tertiary uplift. So I think there's a lot of tertiary geomorphology and tectonics to be done in Britain. I'm convinced of that.
Great. Thank you very, very much, John. The next talk in this session, yes, Richard Gordon has managed to sneak in again. If you hadn't noticed, he assured me it was his twin who spoke yesterday. So we have plate tectonic approximation and update. Over to you. You're okay with this time, aren't you?
Thank you. Okay, so yesterday we heard quite a lot about, the original vision of plate tectonics, much of which still stands in terms of the plates being rigid and the boundaries being narrow. And so I want to talk about some aspects in which one or the other of those assumption isn't strictly true anymore. So, and about 20 years ago, I wrote a paper called The Plate Tectonic Approximation. And so this is an update to that. And in that earlier paper, I emphasized the fact that we had a lot of boundaries, not only in the continents, but also in the oceans that were not narrow. And so sort of the two key concepts, tenets of plate tectonics, classical plate tectonics, if that's not an oxymoron, plates are rigid and the boundaries are narrow. So let's look at the narrowness of the boundaries first. So this is kind of a sketch map of world plate boundaries, slightly updated from one that I did more than 20 years ago. And so, we've heard a lot about the narrow boundaries in the oceans, but early on, many workers, including Peter Molnar, Paul Taquinier, some of Dan's work, Tanya Atwater, recognized that when the plate boundaries go through the continents, they're often wide and diffuse and not narrow at all. But for a long time, many people would contrast that with say, well, unlike in the oceans where the plates are all rigid and the boundaries are narrow, in the continents, the boundaries are diffuse. And one of the things that we were able to establish when I was at Northwestern with my colleagues and students there and workers at other universities, so there are a lot of places in the oceans where the boundaries are also diffuse and not narrow at all. Ball and Harrison wrote a paper about the diffuse boundary between North America and South America, all the maps we've seen so far show a little narrow line that divides them, but nothing on the actual Earth follows those lines. They're completely fictitious. The outstanding example occurs in the Indian Ocean. We often talk about an Indo-Australia plate. I still see this term used in lots of talks, but in fact, what we used to think of as being the Indo-Australia plate really has 4 different plates which we can measure their relative motion. One is the Indian plate up here, another is the Capricorn plate up here. The biggest is the Australia plate, and then this little piece down here, the Macquarie plate. An interesting thing about, and so these are then, the India and Capricorn are divided by a diffuse boundary here. Capricorn and Australia are divided by a diffuse boundary here. Australia and Macquarie are divided by a diffuse boundary here. And for each of these 3, in our best estimates of what the pole of rotation is between these plates, the pole of rotation between India and Capricorn is right here in the middle of the boundary. In fact, I show a gap in the boundary because the strain rates are so low that we don't get earthquakes, observable deformation. But over here we have divergence, over here we have convergence. Similarly, between Capricorn and Australia, we have this diffuse boundary here. Pole of rotation is right here in the middle of it. Have divergence here and convergence here. And then Macquarie plate, we also have the pole of rotation right here, switching from divergence on one side of it and convergence on the other. In each case, it's distributed deformation. So this is very unlike the poles of rotation for the narrow plate boundaries, where the poles tend to be a fairly remote distance in general from those plate boundaries and never lie right along them. So here, rather than just simply being a mathematical convenience for the description of the relative motion, it seems to have some physical significance or geological significance, since it divides the region of divergence from the regions of convergence. We also think the North America-South America pole of rotation is roughly here. So I want to spend a few minutes talking about some recent work I've done with Greg Hausman, trying to model the deformation that's in these diffuse plate boundaries in the Indian Ocean. And what we're doing is we're using the thin viscous sheet models, originally from England and McKenzie, which were meant to help describe and model the diffuse plate boundaries in the continents, the big continental deforming zones. And so I argue, along with Greg, that they work just as well in the oceans, perhaps even better in some ways, because the rheology, the vertical stratification of the rheology is simpler than in the continents. And so here is the domain that we analyze in our finite element is outlined by red right here. We didn't take all of Australia just to reduce the computational burden, and because we're focusing on the deformation here in the Indian Ocean. And we've plotted out the earthquake mechanisms. Instead of showing the actual mechanisms, we've just divided them into 3 sets, depending upon which they most closely resemble. Normal faulting by white circles, thrust faulting by black circles, and then strike-slip faulting by these red circles. So you could see here, in the case, here's our Indian plate. This is roughly where our boundary is between India and Capricorn. Normal faulting here, thrust and strike-slip faulting over here. I think we used the pole of rotation up here, but I think a better estimate is down here. Similarly, for the boundary between the Capricorn and Australia plate, normal faulting here, thrust and strike-slip up here, the pole of rotation is in between them. And so then we applied kinematic boundary conditions. We have good estimates of the relative motions of these, and then we just, at least in our initial analysis, only had one adjustable parameter, and that was what was the exponent that we assumed for the power law fluid that we're using to represent the rheology here. And so that leads to a suite of models in which this is vertical strain rate. This shows the velocities that we applied. This diagram should be in a reference frame that's halfway in between the India motion and the Australia motion. So we see that India moving this way, Australia moving this way. These are contours, non-dimensional strain rates. The red end is contractional in this case. Is that right? Yeah. And then we have extensional kinds of deformation here. N equals 1 it doesn't resemble the actual zone at all. It's too diffuse. N equals 3 also doesn't resemble it very much. N equals 10, we're getting closer. N equals 30 is the best fit. I'm not going to go into the details for lack of time of how we fit that, but it best agrees with the observations of how wide that deformation is distributed in the central Indian Basin. And then N equals 100 right here, the deforming zone sharpens up. But it never looks like a narrow plate boundary no matter what. The physics of it really wants it to be these big wide deforming zones. Okay, and this is just, this is the second invariant of the strain rate tensor here. So we see the strain is heavily concentrated in these two join convergent zones, and then these disjoints, extensional zones here and here compare with the earthquakes. I think we could match the location a little bit better with a different polar rotation right here. And then this compares it with the predicted focal mechanisms. We introduced another adjustable parameter, which was essentially how much extra flux we put down this trench relative to just simply interpolating. We had to put some flux into it corresponding to slab pull, if you like, and this way we would predict a mix of strike, slip, and thrust with more strike, slip, and thrust. Then we move towards strike, slip, and thrust between these contours, but more thrust than strike, slip, and then we cross over into a combination of strike, slip, and extensional faulting on the other side. And so considering just two adjustable parameters, I think this works really well. Okay, moving on to the rest of my talk, because I'm sure my time limit's going to be strictly enforced, 5 more minutes for the next 45 slides, but I'm sure I can get through it. Remaining central tenet of plate tectonics, let's talk about the plates are rigid. Okay, well, no real object is truly rigid, so how fast do plates deform, strain? I mean, it's not a qualitative question, it's a quantitative one. They have to be deforming. So how does this plate tectonic approximation work? How do these strain rates compare with those in diffuse plate boundaries, with those in narrow plate boundaries? How is this straining distributed spatially? What are the main processes by which they deform? So we're talking about the interiors of the plates, not the ones that we want to be part of diffuse plate boundaries. The examples of how we know this is that when we do plate motions around the globe and try to sum them up, North America to Nubia to Antarctica, back to the Pacific plate, back to North America, they don't quite match. They miss by about 5 millimeters a year when we do the global circuit. So how is this 5 millimeters a year if it's real distributed around the world, and what causes it? Also, we have triple junctions that fail closure. Bouvet fails by a few millimeters a year. Galapagos fails by 14 plus or minus 5. That's a 95% confidence limit. It's huge. It's really hard to do this with interplate strain. I think we're probably missing something else. But it remains that when we test plate tectonics, there's places where the rigidity hypothesis fails. Okay, so the plates aren't rigid. What could cause the non-rigidity? Two possibilities that we explored. One is plate movement over a non-spherical Earth. Dan first pointed this out in a paper in 1972, and Turcotte and Oxford also looked at it a bit. And the other is horizontal thermal contraction of oceanic lithosphere. We are well acquainted that we see the subsidence of the lithosphere from the thermal contraction. It's contracting in all three directions, not just one, so the plates have to be shrinking horizontally. How big is this? How big are these strains? So here's just a kind of a order of magnitude loose look at this. Narrow plate boundaries, in terms of millions of years, we have strains of 10 or 100 or so per million years, super high strain rates. Stable plate interiors, the lower bound here comes from the earthquake moment release, and as we've heard sometimes, the actual deformation can be a factor of 10 or even 100 higher than the seismic moment release, so that might bump it up to here or up to here. If we pick this, we can see that we're from -5 to +2, 7 orders of magnitude difference in the strain rates between narrow plate boundaries and our rigid plate interiors, and that's why the rigid plate approximation works so well. Non-sphericity, when we look at that, we can get strains up to about 10 to the -3 per million years. We can compare that with, say, the strain rate in the Tibetan Plateau, which is between 1% and 10% per million years, or in the diffuse oceanic plate boundaries, which are about peaking at an order of magnitude slower, 1% per million years. Thermal contraction of the oceans is age dependent, and in the youngest lithosphere, we can get very high strain rates. Okay, 2 minutes for the last 39 slides. We can do this. So, okay, here's a map of strain rates we've estimated for the non-spherical Earth. The fastest straining plate is Australia because it sits at mid-latitudes and it moves north quickly. We'll move on quickly to the next one. Thermal contraction, it's about, goes like 1 over the age in terms of what the strain rate is. If we plot it up, it looks like a seafloor age map. The highest contraction is near the ridges, and then it gets lower. It gets above 10 to the minus 3 per million years, almost up to about 10 to the minus 2 at the ridges, 1% per million years, like the peak rates we see in the diffuse oceanic plate boundaries, and then gets really low in the older oceans, and in the continents, we're just kind of neglecting it. This is the strain rate for the Pacific plate where we force it to satisfy strain compatibility. 2 different end member assumptions. Won't go into them. If we integrate them to get a velocity field, they look very similar. If we fix the old plate, part of the plate, we get rates of up to 2 millimeters a year at the other end of the plate. If we put it in a reference frame by the Pacific Antarctic rise, which is relevant to our plate circuits, then we get these kinds of motions up here, a couple millimeters a year. So how can we further test the predictions of the shrinking plate hypothesis? Hard to do it with geodetic data because it's hard to get enough sites in the right places on the oceans. Turns out the azimuths of transform faults are sensitive to this. It predicts that transform faults don't exactly parallel plate motion. They're off by about ½ degree on average. It's not a big effect. The difference between right lateral and left lateral is predicted to be about 1 degree different. What's hard to measure it this well, Dan reviewed the paper on this, and he said he didn't believe any of it, but it should be published anyway, so I'm very grateful for that. Here we're comparing blue and red. Blue is right lateral, red is left lateral. Here's the 6 plate pairs where we have both right and left lateral ones. If you average them out in every case, the left lateral is clockwise of the right lateral. 6 out of 6 for a coin flip. I'll take those odds. And this was from the Demetz et al. Analysis. We weren't thinking about what the transform faults should be when we did this, and so I don't think there's any bias. Okay, we're down to 5 seconds, so I should go to my last slide. So some conclusions from the talk. Many plate boundaries are not narrow but diffuse. Diffuse plate boundaries occur in both continents and oceans, cover 10 to 15% of the Earth's surface. Transform faults are not parallel to plate motion, but it's a really good approximation. Plates are not rigid, but it's also a really good approximation. Lateral thermal contraction of plates likely sums to 1 or 2 millimeters a year across every plate. Range of strain rates from horizontal thermal contraction and plate movement over a non-spherical Earth overlap, but the thermal contraction is bigger in the younger oceanic lithosphere. Thank you very much.
Thank you, Richard. So again, I'm afraid we literally have no time for questions, but no, Dan will respond as to why he let a paper through and didn't agree with it in the discussion, not now. So you have time to prepare your response. All right, next up, we're going to East African transform margin, a very interesting part of the world, and we're using potential field geophysics, and I'm pleased to welcome Andrew Long. So that's your light. That's your light, and forward and backwards.
Okay, thank you everyone. Great pleasure to be here, and I guess part of my job is to try to keep you awake for at least another half an hour, which I hope to achieve. So last year I learned how to draw curvy lines over gravity and magnetic data, which doesn't tend to happen very often. You normally end up with lineations sort of like this. So hopefully I'm going to be able to explain to you why I'm doing that. And the interpretation that I have, and it's an interpretation, it's not a model, so it hasn't been manipulated to derive or to approve or conclude a preconceived idea, whether that be a geological idea or any other idea. And hopefully you'll understand a little bit more what I'm talking about when I actually get into that. So I've probably already had about 5 minutes already. So you're going to see this thing come up several times through the presentation, and we're going to work from the top down, from north to south. The little boxes and the lines indicate the areas that we're going to be looking at as we progress down the transform margin. So the first thing I'm going to do, take you through a very brief description of the data that we're working with, and then I'm going to talk about echelon structure, then the correlations, and the conclusions. So the two different types of data that we're working with, complementary, both satellite data. One is the enhanced magnetic field model, 56 kilometer resolution, wow. But it beats 10 degrees of paleomagpoles, I guess. So the idea is that we process that correctly for the IGRF year and reduce it to the pole, amplitude gain correct it, so it tells us something useful about the deep crustal magnetization, something that can be directly correlated to geology. With the Samuel-Fourier gravity, again, just systematically processed to derive something useful which will be directly correlatable to the shadow crustal density variation. So this is one of the two key messages that I want to get across. It's an excellent opportunity to remind people that Samuel-Fourier gravity data is incredibly easy to acquire, but unfortunately it's also incredibly easy to abuse in terms of trying to prove or disprove or to illustrate an interpretation. So yeah, Fourier gravity, it directly correlates to topobathymetric relief. So it should be correctly processed to yield something slightly more useful that directly correlates to geology and geological structure. And I mean, it's probably been said before, at least in this way, but you should let the data speak for itself. So it's not just for the people gathered here. Hopefully this is going to go online. And for all those people that are using Fourier gravity and modeling just some densities to derive something to support some preconceived model, that this is what I'm telling you, because all the work in this presentation is derived from just essentially the bare minimum modeling input. There is no real modeling. And the same goes for the EMAG2. Lots of people are trying to use magnetics in offshore East Africa in the Indian Ocean. But at the end of the day, you have to consider what data is available. We can see that these lines are very sparsely sampled in the Indian Ocean. This is a problem that there is in determining the extent of the spreading center in the Western Indian Ocean, where the translations, where the transitions between continent and ocean occur, and so on. And also with the version 3, we can also get access to an idea of the type of the source of the data. So I'm sure it's actually not too bad at all. Mostly GTEC data. But as we go offshore, we get lots of pink sort of no data areas onshore and all this stuff. I mean, it has to be made up. It has to be interpolated. It doesn't have any scientific significance if it's just blank data. So that's why I like using the enhanced magnetic model. It's only been around for a couple of years, but it provides a coherent and homogeneous field from which we can process it and then make proper interpretations. So this, I mean, I could give some history on the interpretation, but basically it's all happened this year. And what we have here are 4 blocks which really stand out, and they're right stepping as we're going from south to north in an on echelon arrangement. And yeah, I mean, you could interpret that in a number of ways, but it is actually strongly suggestive of duplexing, especially if you are aware that people are talking about other intraplate strike slip structural components, such as John Dewey was talking about earlier, with transpression in the north and transtension in the south. So I'm going to take you through a very brief, I don't know how many minutes I've got left, but a very brief rundown, starting from Anza in the north, where I would like to believe that the transitional margin propagated from underneath Anza. It's a very deep, thick basin. It's got a thick Cretaceous sequence. You can't really see below that. That's already been commented. We don't know what structure lies underneath it. The 2 key components of the transitional margin to point out is 4, which is, 3, which is the main transitional margin. And this coming in here is the oblique rifted passive margin of the Lamu embayment as we're coming offshore. And then we're into the inside of the transitional margin. And you could almost perceive that Anza has been rotated through geological time. To build on that, the comments, I mean, even yesterday with Cynthia Ebinja talking about the periphery of cratonic areas remaining zones of weakness, and even earlier, for several decades, people have been emphasizing the same point. Well, if we take some of this work here from Fritz, 2013, and he's mapped out areas which resemble the suture zone between the cratonic West Gondwana and the incoming Azania of East Gondwana, of which Madagascar down here on the right is said to be partially comprised of as well. So, and you fit it all back together, well, Anza is directly over that. So there may be a suture zone underneath Anza at a very great depth. So that's something to think about. That we know that the faults within the Anza Basin have been moving all the way through the history of the Gondwana breakup and the rift and drift and of Madagascar to the south, and into the tertiary where there is evidence of reactivation of faults compression. So there are at least 2 phases of compression which affect the structure to the west of the Davy Walu Ridge, where we broadly have this sort of area of transpression. So going south from the area of transpression, well, we'll stay 5 minutes, okay. So this is the area of transpression here. The gravity shows an oblique fold axis, which is probably related to the earlier transpression, and then this horsetail splay can be clearly mapped. Okay, going further south into the duplex zone, a nice regional line from iron going from just south of Songo, right out into the oceanic margin to here, And I'd just like to point out the outer high, which correlates with the magnetic high here. And this is the main margin, this is oceanic crust. All of this is continental crust. So believe that if you will. That's what I'm going to say there. The Corimbus lacerda, so we're going from the duplex to the transtension zone. The transtension starts off here, the southern onset, which is just west of the Saint-Lazare seamount. And we also have the last duplex fold zone in here on amber alert. The influence of the East African rift system, I just want to throw it out there that perhaps this isn't an offshore East African rift system. Taking Mugonot's mapped faults, we can see that they have an en echelon arrangement north of the Paisley Seamount, and then to the south, they don't show any offsets. And that's pretty consistent with the duplex fold rotation of the blocks, and then it's just cut off. And the other thing is that further south, there's absolutely no rotation. They're locked into the transtensional structure. Seismicity, can't leave seismicity out. This is from Mulabo from last year, and we can see how even some of the seismicity along this fault here, this antithetic fault, going through the northern Mozambique belt, ties in with everything on the margin, the western margin of the strike slip corridor is locked. All the seismicity is locked on the onshore western branch of the East African rift system. And so on. I could go on, the transpressional responses. A couple of lines from TGS, just to demonstrate that north of the Caledonides seamount, we have a pull-apart feature, if it's EARS or not. And then south, we don't have any deformation, we just have the Davy Ridge fold axial hinge running straight down. And then what is happening today, so the strike slip fault is diverted to the east, and why should that be? Something happened during the Cretaceous. So this is it's always difficult showing large structures which strike north-south. So we're looking west, and we haven't mentioned anything about plume theory. Okay, and but where these plumes are said to have tracked, and Colin Breeze used them in his work, the Marion plume is here. There's very clearly a very distinct signature to the trail of where these plumes are meant to, especially when you look at the difference between the oceanic spread, the crust from which Antarctica departed. So those are the conclusions. You can read them for yourself.
Thank you. Thank you.
Okay.
One quick question. No one. Well, we can catch up our missing time. Thank you. We can hold questions till the session at the end. So, off you go.
I would like to ask, I'll put a question to John. This might need your chairmaning skills to control John. But it's a general question. I mean, when plate tectonics came out, talk about the oceans, it hasn't required very much modification since those early times. And it offered a great promise of doing something with understanding continental geology, and the early iconic papers by John and his colleagues had a go at that. I'd be interested to know your perspective on what it didn't do. So one of the interesting problems that you and John Casey referred to, for example, was ophiolites. And are we really any nearer now understanding how you get a bit of ocean crust from several kilometers below sea level onto a continental margin? Or is that one of the problems which has remained, as intractable now as it was then?
I don't think so. I think that I think that the ophiolite problem is, never use the word solved, that's an absurd term to use, but nevertheless I think we've got much further with understanding ophiolytes using the model that Jack described today. I mean, there's no question that geochemically the bulk of ophiolites have boninites in them. Now there are scraps, what Schenker used to call ophiurags, the little bits and pieces of ultramafics, little pieces of gabbro. Call them ophiolites if you want to, but I would discount those things. I wonder if...
Answer a very specific question, which is how does it happen? Is it happening anywhere today? How do you get a bit of seafloor from several kilometres below sea level above sea level?
I think
like
the...
special cases, don't they, all the ones we know?
I think that the abduction of ophiolites is easiest if a forearc hits a continental margin. Then there's a ready-made simple mechanism for doing it, stuffing a rifted margin underneath an arc. If you like, a partial abduction, a collision of an arc and the abduction of the forearc on top. That's what it looks like in West Newfoundland. There's a huge sheet, several hundred kilometres wide, all the way from the middle of Newfoundland, if you like, right out onto the platform. You can see it going right out across the rifted complex, and that's something you could map. You can actually see it. And that ophiolite is very clearly part of an arc. That is, there are interlacing relationships between transforms and arc rocks, ophiolitic rocks. They're all bound, as Jack showed on his diagrams, by the uniform orientation of the sheeted dike complex. That's always across the whole system. It averages northwest southeast. So it looks like a coherent slab, a couple of 100 miles wide, that abducts onto the continental margin, and it clearly is part of an arc. So I'd say that most ophiolite complexes are in that situation. There may be others. The Tatayo complex in Chile, for example, is on a ridge trench triple junction. There may be ways of doing it, special little bits here and there, but the big abducted ophiolites scattered around the world, mostly Jurassic, Cretaceous, and Ordovician, all about those three ages. I think that then you've got to have a continental margin available. Yes. You asked me to ask the question. I'm trying to do it.
I think we can talk more than about ophiolites. So Bob White would like to ask a question.
To Richard Gordon.
Good.
You showed us that there were earthquakes in the south of India, in that broad deformation zone, and you had predictions for the directions of slip from your model, but you didn't show us the slip vectors from the earthquakes. Do they match your model predictions?
Oh, you mean where I didn't show what the actual mechanism?
Well, you just said they're normal or thrust or strike slip, but therefore you must know what the slip vector is. And does the slip vector match your model of distributed deformation?
Well, I mean, in a very general way, the slip vectors do, but we don't expect in distributed deformation, we don't expect the slip vectors to line up with it. You know, it's because you've got a combination of the displacements and the rotations of the blocks. But I mean, in a general sense, in the equatorial Indian Ocean, in that zone between the India and the Capricorn plate, the normal faulting is north-south extension, which is what you would expect. And in the central Indian Basin, the mechanisms where we have thrusts or north-south contraction, and the p-axes and the strike-slip faults in that same region line up that way. But as you get closer to the trench, they become more northwest southeast. There's a bit of a rotation, but I don't think it's inconsistent with it. You know, we also
competition.
Yeah, I mean, but you're also transitioning over to what's really arguably the boundary between India and Australia, since the convergent zones merge together. But the slip is also, the deformation is also affected by the presence of the trench. But I mean, it's still all is consistent with adding up with what we think is the relative motion between the three plates.
Nice question. Nice, thank you. Anybody else have a question? Okay, I'd like to ask one too, but you can go first.
Can I carry on with you? Because as far as I could see from your models, 90
Say
East
your
Ridge.
name again.
Oh, sorry, Jim Chalmers, Geos, Copenhagen. As far as I could see from your models, 90 East Ridge crosses the middle of one of your postulated plates. Can you suggest what is 90 East Ridge in your model?
was on.
Oh, thank you so much. Well, I mean, so 90th Ridge is a volcanic constructional feature. It's not a deformational feature, and it looks, you know, in the early days when we were looking at this, we thought that some of the deformation may be localized along the 90th Ridge, along the transform fault next to it, but it doesn't seem to me at this point in time to be very important if a little bit of localization is there, because the deformation cuts right across 90th Ridge. I mean, it's just something else that's being deformed and strained as part of the deformation.
I think Dan would now like to ask a question.
I didn't, Dan McKenzie, I didn't understand what the boundary conditions were on the models that you showed with different end powers, as to whether you fixed the velocities on the boundaries or whether you were fixing the forces.
Oh, we were definitely fixing the velocities on the boundaries. We did not try to do the forces, which is a much harder problem. And we know reasonably well what those angular velocities are. So I rushed through it, but we had an outline around, say, India, the Indian plate portion, and we forced that boundary, the edge of the plate, to move rigidly, and then across wherever we went across a diffuse boundary, then we just tapered, say, from India to Capricorn, and then it was a little bit of rigid Capricorn at the edge, and then Capricorn to Australia, we tapered that as well. And we had a big taper across the Java-Sumatra Trench as well, which, you know, for the initial models, and then along that boundary, we made it more complicated because we did experiment then with adding an additional flux into the trench, superimposed on interpolating between India and Australia.
Because what struck me was that actually the deformation that you were finding looked like the deformation you'd expect, right, from trying to drive the whole thing northwards by pulling, right, in the Sumatra Trench. And I rather wondered whether you'd actually looked at the force balances on that plate to see whether that was in fact where it broke, where it would break, because it looked to me as if it was, and if it would break in the way that you saw.
Yeah, so, I mean, we did do a retrospective looking at what the stresses were, you know, in the model that were a consequence of the displacement bound, the velocity boundary conditions we put on it. Not sure I would trust them completely. It doesn't look like we necessarily got them right up in the northern part of the Indian plate exactly, but so we most trust the region where we have the deformation focus, not so much the far field.
I think you could both perhaps continue that offline.